Today we will be learning how to calculate the pH of a solution from the hydrogen concentration and vice versa using strong acid, strong base reactions. First, let's get a basic understanding of how acid-base titrations work and a better understanding behind the calculations.
As a general overview, the pH of a solution is based on the pH scale between 1 and 14 and is a measurement of how acidic and basic a solution is. The term pH refers to the potential of the hydrogen ion. As we will be exploring titrations of strong acids and strong bases, it is important to note that both the strong acid and base fully dissociate. At equivalence, the resulting pH will be 7, unlike the equivalence for reactions involving weak acids and weak bases. A pH of less than 7 is considered acidic, equal to 7 considered neutral, and greater than 7 considered basic. For strong acid and strong base reactions, a strong base or acid react, resulting in a pH, which measures the resulting hydrogen concentration in the solution. A higher hydrogen ion concentration results in a lower pH, whereas a lower hydrogen ion concentration results in a higher pH.
Now for the actual calculations, which are fairly simple once you are familiar with the equations. The equation for calculating pH is as follows. pH equals negative log of the hydrogen concentration. The pOH can be calculated by subtracting the pH from 14. For example, if the pH is 4.7, the resulting pOH would be 9.3. To determine the hydrogen concentration from pH, use the equation H equals 10 to the negative pH. It is also useful to understand that by multiplying both the hydrogen concentration and the hydroxide concentrations, the result will always be 1 times 10 to the negative 14. The first question we will look at is find the pH of a 0.0025 molar HCl solution. HCl is a strong acid and is 100% ionized in water. The hydrogen concentration of this solution would be 0.0025 molar. To find the pH of this, we would have to use this equation. So all we have to do is plug in this number into this equation. And there's your answer. For our next question we have, if a soil solution has a pH of 4.7, what is the hydrogen concentration of the soil solution? In this instance, we already know the pH, so we just need to find the hydrogen concentration. So what we do is we use the equation So since we know that the pH is 4.7, we just have to plug that into here. And there's your answer.
Now for a more complicated question. Calculate the pH of a 0.5 NaOH solution. As you know, NaOH is a strong base. This means it dissociates completely and needs to be manipulated to find the pH. So first let's calculate the pOH. Calculating the pOH is like calculating the pH. You negative log the concentration of the base. So the concentration of the NaOH is 0.5. And to get that, you just put in your calculator. So negative log of 0.5 equals 0.3. And from there, you just subtract it to 14 to find the pH. So pH equals 14 subtract the pOH, which is 0.3. And from there you get 13.7. And that's your answer.
For our last question we have, what is the pH when 48 milliliters of 0.100 molar NaOH solution have been added to 50 milliliters of 0.100 molar HCl solution? Because this is a strong acid-base reaction, we want to use this equation. H plus aqueous plus OH minus aqueous into H2O liquid. First, we want to find the number of moles in the HCl solution. We can find this by multiplying this and this. We would convert this into liters from the milliliters and multiply this by 0.100 molar, and this would equal 0.005 moles of HCl. Next, we want to find the number of moles in the OH. So we multiply this number by this number. Again, we will convert into liters. This will become 0.048 liters times 0.100 molar equals 0.0048 moles of NaOH. This would result in a difference of 0.0002 moles of H+, aqueous. The total volume of the solution would be 0.048 liters plus 0.05, and this would be 0.098 liters. To find the hydrogen concentration, we want to find moles over liters. So we put this here over 0.098 liters, and this would equal 2.0 times 10 to the negative 3. And to find the pH, as we have shown you before, we would use this equation and plug in 2.0 times 10 to the negative 3, and the pH would be 2.69.